Late autumn, 1943. Aberdeen Proving Ground, Maryland. An M4A2 Sherman tank with standard 16-inch wide rubber chevron tracks rolled toward a muddy test course, churned deliberately into soup by repeated watering over 3 consecutive days. Engineers from the Ordnance Department gathered along the sidelines with clipboards, stopwatches, and measuring instruments. Behind this seemingly routine trial lay growing alarm from commanders in Italy, where German forces had flooded entire valleys during their retreats. American tank battalions found themselves immobilized, watching Panthers and Tigers maneuver across terrain that left Shermans belly deep and helpless. The solution would not come from exotic new suspension systems or revolutionary engineering. It would emerge from a deceptively simple modification, a sheet metal extension welded to standard track connectors that would transform Sherman mobility in conditions German tankers assumed would stop any Allied armor. The mathematics of ground pressure were about to be rewritten, not through complex calculations, but through practical field improvisation that German engineers, obsessed with precision and theoretical optimization, would never have considered acceptable for frontline deployment. This single modification, dismissed by some ordnance officials as too crude for serious consideration, would give American armor capabilities in mud and snow that no Panzer division could match. The test Sherman ahead, designated for comparative trials against a captured Panther, represented the culmination of months of desperate field reports and improvised solutions from tank battalions fighting across Mediterranean terrain. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The Sherman accelerated toward the obstacle course, its engine note steady and familiar. The Continental R975 radial engine, inherited from aircraft design and proven across tens of thousands of production tanks, delivered consistent power. Standard tracks bit into hardened ground at the course entrance, then met the deliberately churned mud. Resistance increased immediately. The driver downshifted, engine revs climbing as track cleats fought for purchase in slippery soil mixed with standing water. Forward momentum slowed, then stopped. Track blocks spun, throwing mud in arcs behind the vehicle. The Sherman settled deeper, its narrow tracks unable to develop sufficient flotation or traction. Engineers marked the stopping point with surveying stakes, 20 yards into the 80-yard mud field. A second Sherman approached, identical in every specification except one detail that transformed its capabilities fundamentally. Extended end connectors, unofficial Army designation, duckbills, projected several inches beyond the standard track width on each link. These sheet steel extensions, welded to normal track connectors in pairs, effectively widened the 16-inch standard track to approximately 21 inches without requiring new suspension components, drive sprockets, or idler wheels. The modification looked crude, almost makeshift. German engineers examining photographs later would describe them as typically American, meaning simple to the point of appearing unrefined, lacking the precision and mathematical elegance German doctrine demanded. The modified Sherman entered the mud field at identical speed to its predecessor. Its wider tracks distributed vehicle weight across substantially increased surface area, reducing ground pressure from approximately 14 pounds per square inch to under 11. That difference, seemingly modest in abstract calculation, proved decisive in practical application. The Sherman maintained momentum through sections where the standard vehicle had stalled. Track cleats gripped wet soil more effectively, the wider contact patch preventing individual track blocks from simply cutting through the mud surface and spinning uselessly. The tank crossed 40 yards before slowing, then 60 yards, finally 80 yards, emerging onto solid ground on the opposite side, while the standard Sherman remained mired behind it. Engineers recorded temperatures, fuel consumption, engine stress readings, and track wear patterns. The extended connectors showed no signs of unusual stress despite their apparent fragility. What they did show was battlefield practicality that no amount of theoretical engineering could have predicted or properly evaluated without actual mud testing under field conditions. This was automotive problem-solving from an industry that had spent decades building vehicles for American roads, farms, and construction sites. Practical solutions that worked reliably mattered infinitely more than elegant designs that performed beautifully on paper but failed when dirt, water, and battlefield conditions intervened. The Aberdeen trials in late 1943 represented only one phase of intensive development work that had accelerated through that year as American forces pushed deeper into Italy and prepared for the inevitable invasion of northern Europe. The Sherman suspension and track system had seemed entirely adequate during development and initial combat operations in North Africa. 16-inch tracks provided reasonable flotation for the 30-ton vehicle on firm ground. The vertical volute spring suspension, with its paired road wheels and robust bogie units that could be unbolted and replaced as complete assemblies, offered reliability and ease of maintenance that German torsion bar systems could not match. But North Africa presented mostly firm desert terrain, with occasional mud after rare rainfall. Italy introduced conditions American tank designers had not adequately anticipated. Autumn rains turned river valleys into expanses of deep mud. German engineers, familiar with Eastern Front conditions, where Rasputitsa, the muddy season, immobilized entire armies, recognized these tactical opportunities. Wehrmacht units systematically destroyed drainage systems and diverted watercourses to flood approach routes before retreating. They understood that if they could not stop American armor through firepower alone, they could immobilize it through environmental conditions that exploited inherent design limitations. Field reports from Italy through late 1942 and early 1943 documented increasing mobility problems. Tank battalion commanders noted Sherman crews avoiding muddy areas that German vehicles traversed without difficulty. The Panzer IV, with its wider tracks inherited from earlier models designed specifically for Eastern Front service, maintained mobility in conditions that stopped American armor. The Panther, despite its significantly greater weight approaching 45 tons, featured even wider tracks and sophisticated torsion bar suspension that distributed ground pressure more evenly than the Sherman's basic VVSS system. Most frustrating for American crews, captured intelligence indicated that German tankers had been explicitly briefed on Sherman mobility limitations and instructed to exploit them tactically. Ordnance engineers recognized the fundamental problem lay in ground pressure, the vehicle weight distributed across the track contact area. A Sherman weighing approximately 33 tons, fully loaded and fueled, running on 16-inch tracks with roughly 95 inches of track length in contact with the ground per side, exerted ground pressure around 14 pounds per square inch. This exceeded the threshold at which most soil types, particularly when saturated, could support tracked vehicle movement without excessive sinking and loss of traction. The Panther, despite weighing 45 tons, achieved ground pressure around 12.8 pounds per square inch through its significantly wider tracks and longer contact length from its 8-wheel suspension. The mathematical solution appeared straightforward: increase track width to reduce ground pressure, but practical implementation confronted substantial obstacles within American tank production infrastructure. The Sherman utilized 16-inch tracks specifically because that width represented the maximum that could pass between the vehicle's bogie wheels without requiring suspension modifications. Adopting truly wide tracks comparable to German practice would necessitate redesigning the entire suspension system, a process requiring months of engineering work, retooling production facilities, and interrupting Sherman manufacturing at precisely the moment when production rates had reached unprecedented levels, with more than 2,000 tanks per month rolling from multiple factories. Ordnance Department planners faced a classic wartime dilemma: the theoretically superior solution, a completely new wide-track suspension system designated HVSS, or horizontal volute spring suspension with 23-inch tracks, was already under development. Prototypes had reached Aberdeen for testing by spring 1943, but transitioning production, training maintenance personnel, and shipping replacement parts to support two entirely different suspension types simultaneously would create logistical chaos. More critically, any production disruption meant fewer tanks reaching units already engaged in combat operations where numerical superiority determined tactical success. The alternative approach emerged not from Detroit engineering offices or Aberdeen test ranges, but from field maintenance units in Italy, working directly with tank crews who understood their mobility limitations intimately. Ordnance sergeants examining track assemblies recognized that the end connector design, the component that held individual track blocks together while allowing the assembled track to articulate around sprockets and road wheels, could be modified without changing any other vehicle components. A sheet metal extension welded to each connector would effectively widen the track without requiring new drive sprockets, idler wheels, suspension components, or hull modifications. This field improvisation violated normal engineering practice in multiple ways. The extensions added unsprung weight, mass attached to the tracks rather than supported by the suspension, typically considered undesirable because it increased stress on running gear components. The welded joints introduced potential failure points, particularly in designs using relatively thin sheet steel rather than forged components. The extensions projected beyond the track width, making them vulnerable to damage from obstacles, debris, or contact with hard surfaces during road marches. German engineers examining captured Shermans fitted with these devices would enumerate these deficiencies exhaustively in technical reports, concluding that while the modifications demonstrated typical American pragmatism, they represented suboptimal engineering unworthy of consideration for Panzer development. But field testing revealed what theoretical analysis missed. The extended connectors worked reliably under actual combat conditions. They improved flotation measurably in soft terrain. They were easy to install, easy to replace when damaged, and compatible with existing maintenance procedures and spare parts inventories. Tank crews could install them at battalion maintenance facilities without specialized equipment or extensive technical training. When extensions broke off, which occurred regularly when tanks maneuvered over rocks or operated on paved roads, standard connectors could replace them immediately using existing supply stocks. This serviceability, this practical maintainability by ordinary soldiers with basic mechanical training, exemplified American automotive engineering philosophy developed through decades of civilian vehicle manufacturing. By mid-1943, multiple variants of extended connectors were in field testing across Mediterranean theater units. Some used flat steel plates approximately 4 inches wide, increasing total track width to 20 inches. Others employed angled extensions designed to provide additional traction through improved cleat geometry. British engineers, working parallel to American development efforts, created their own variants with different attachment methods and dimensional specifications. None of these represented formal Ordnance Department programs with official designations and standardized procurement specifications. They were field modifications, local solutions to immediate tactical problems, spreading through tank battalions as word circulated that certain units had developed methods for improving mobility. The Ordnance Department's role evolved from attempting to control and standardize these modifications to recognizing their value and facilitating wider implementation. Aberdeen Proving Ground. Trials in autumn 1943 aimed to quantify actual performance improvements and identify which variants offered the best balance of mobility enhancement, durability, and ease of production. The tests employed systematic methodology designed to replicate battlefield conditions tank crews would encounter during the planned invasion of Northern Europe. Engineers constructed obstacle courses, combining multiple terrain challenges. Steep slopes with soft approaches tested power and traction simultaneously. Ditches filled with standing water and soft bottoms evaluated flotation and ability to maintain momentum through difficult transitions. Open fields deliberately watered and churned replicated the farmland conditions expected across northern France and Belgium. Comparative testing included not just different Sherman variants, but captured German vehicles to establish objective performance baselines against enemy equipment. The captured Panzer, a relatively early production OSV-D model seized in Sicily during summer 1943 and transported to the United States specifically for technical evaluation, represented the most capable German armor American forces would face in significant numbers during coming campaigns. Aberdeen engineers had already conducted exhaustive mechanical testing, documenting the Panther's automotive characteristics. Its wide tracks, sophisticated suspension, and relatively low ground pressure despite heavy weight made it a formidable benchmark for mobility comparisons. Initial comparative trials in November 1943 produced results that ordnance officials found both encouraging and concerning. The standard Sherman with 16-inch tracks performed adequately on firm ground but struggled in deep mud, confirming field reports from Italy. The Sherman fitted with extended end connectors showed substantially improved performance, crossing obstacles that stopped the standard vehicle. But the Panther, despite weighing significantly more, traversed the same terrain with apparent ease, its wide tracks and low ground pressure providing capabilities American vehicles could not match even with modifications. More extensive testing revealed nuances the initial trials had obscured. The Panther's interleaved road wheel suspension, while providing excellent weight distribution and low ground pressure, created serious problems in actual field conditions. Mud, rocks and debris packed between the overlapping wheels, sometimes jamming the running gear entirely. In freezing conditions, this packed material froze solid overnight, immobilizing the vehicle until crews could manually clear the wheels, a process requiring hours of labor in combat conditions. The Panther also demonstrated poor traction despite its low ground pressure, the smooth steel track blocks providing limited grip on slippery surfaces compared to Sherman rubber tracks with their chevron tread patterns. The Sherman with extended end connectors showed different performance characteristics. While it did not achieve the Panther's exceptionally low ground pressure, it combined reasonable flotation with superior traction. The rubber track blocks gripped soft soil more effectively than steel. The chevron tread pattern, borrowed directly from tire design principles, American manufacturers had refined over decades, channeled mud away from the contact patch rather than allowing it to pack and reduce grip. The simpler suspension, lacking the Panther's complexity, proved less vulnerable to clogging and easier to maintain under field conditions. British trials, conducted at their Fighting Vehicle Proving Establishment, tested American extended end connectors alongside British-developed variants designated platypus grousers. These employed different attachment methods and more aggressive tread extensions designed to bite into soft ground more effectively. Comparative testing found both approaches effective, though the American design's simpler construction and easier installation made it preferable for widespread field implementation. British engineers noted that while German tanks theoretically possessed superior mobility on soft ground through wider tracks and lower ground pressure, practical field testing demonstrated that Allied modifications could achieve comparable or superior results through different engineering approaches. The development timeline for these track modifications reflected wartime urgency that compressed normal engineering cycles from years into months. Early field improvisation in Italy began appearing in unit maintenance reports by January 1943. Ordnance Department recognition and formal testing programs commenced by spring. Aberdeen trials produced quantified performance data by autumn. Production contracts for standardized extended end connectors reached manufacturers by late 1943, with first deliveries to European theatre units anticipated for early 1944, just in time for the planned invasion of France. This rapid development cycle, from field problem identification through testing to production implementation, demonstrated American industrial responsiveness that German planning could never match. Wehrmacht procurement processes, bound by rigid bureaucratic procedures and requiring extensive committee approvals for even minor modifications, typically consumed 12 to 18 months between problem recognition and fielded solutions. American automotive industry, experience with rapid model year changes and continuous product improvement, had created organizational cultures capable of implementing modifications across entire product lines within months when necessity demanded. Sherman track development extended beyond simply widening existing components. Engineers examined every aspect of track design, seeking improvements that could enhance reliability, reduce maintenance requirements, or improve operational characteristics. The rubber chevron track, designated T48 in technical nomenclature, had become standard by 1943 after replacing earlier rubber block designs that wore excessively and provided poor traction. The T48 used molded rubber track pads with chevron tread patterns vulcanized to steel bases, providing excellent durability and grip while remaining relatively quiet compared to all steel tracks. Alternative track designs served specialized requirements. The T-47E1 combined steel cleats with rubber backing, offering improved traction on ice and hard surfaces while using less rubber, an increasingly valuable strategic material as wartime demand strained supply. The T-66 all-steel track, developed for vehicles equipped with the new horizontal volute spring suspension and wider 23-inch track width, provided maximum durability but damaged paved roads and created excessive noise. Each variant reflected specific engineering trade-offs between performance characteristics, manufacturing cost, material availability, and operational requirements. The extended end connector, officially designated with part number 7055614 in Army supply nomenclature and informally called duckbill by tank crews, became the most widespread track modification program of 1944. Production contracts went to multiple manufacturers, including established track producers and small fabrication shops capable of welding sheet steel components. The decentralized production approach, typical of American wartime manufacturing, ensured adequate supply even if individual facilities suffered disruptions from equipment failures, labor shortages, or material allocation problems. Installation procedures required minimal specialized training. Maintenance personnel removed standard end connectors from track assemblies, replacing them with extended versions using identical pins and installation techniques. The process consumed approximately 4 hours per tank when performed by experienced crews, less time than replacing a single bogie unit or conducting other routine maintenance procedures. Tank battalions in England preparing for D-Day operations received shipments of extended end connectors through spring 1944, with instructions to install them on all vehicles except those designated for road march. Duties where the extension's vulnerability to damage from paved surface contact outweighed their mobility benefits. Field reports from Italy, where some units had been employing field-fabricated versions since early 1943, provided valuable data about long-term durability and maintenance requirements. The extensions did break off regularly, particularly when tanks operated on roads or rocky terrain where hard objects struck the projecting steel plates. But breakage rarely resulted in mission failures because crews carried spare connectors and could replace damaged units. During routine maintenance halts, the extension's serviceability, their compatibility with existing maintenance procedures and supply systems, proved as important as their performance improvements in determining operational value. German intelligence services collected information about American track modifications through multiple sources. Captured Shermans provided physical examples for examination. Interrogations of prisoners produced descriptions of new equipment and tactics. Aerial reconnaissance photographs occasionally showed details of American tank formations being assembled in England. By early 1944, German tank development offices had compiled reports describing American extended end connectors, analyzing their design principles and evaluating their effectiveness. German engineering assessment concluded that while the modifications demonstrated typical American pragmatic problem-solving, they represented fundamentally inferior approaches compared to proper wide-track suspension systems. The reliance on bolt-on extensions rather than integral track design violated principles of robust engineering. The vulnerability to damage from hard objects indicated inadequate strength in critical components. The acceptance of frequent breakage and field replacement reflected manufacturing philosophy that prioritized quantity and ease of production over quality and durability. What German analysts failed to recognize was that these characteristics, which they identified as weaknesses, actually represented strengths within American operational context. The ability to install modifications using standard maintenance procedures meant tank battalions could upgrade their entire equipment inventory without factory support or specialized facilities. The compatibility with existing supply systems eliminated logistics complications that plagued German forces attempting to maintain multiple incompatible variants simultaneously. The ease of field replacement when components failed meant crews could maintain operational readiness despite equipment damage that would have sidelined German vehicles awaiting specialized repair. More fundamentally, German engineering culture's emphasis on theoretical optimization and elegant solutions prevented serious consideration of modifications that appeared crude or makeshift, despite their practical effectiveness. A properly engineered solution required redesigning entire systems from fundamental principles, creating integrated designs where every component complemented others perfectly. Accepting bolt-on compromises, even when they worked reliably, violated professional standards that German engineers had absorbed through their technical education and professional experience. American automotive engineers, trained through decades of commercial vehicle development, where customer satisfaction and field reliability determined success, approached problems differently. The perfect solution that required extensive development time and disrupted production schedules was inferior to the adequate solution that could be implemented immediately using existing manufacturing capabilities. Continuous incremental improvement, making small modifications regularly rather than waiting for comprehensive redesigns, had proven effective in civilian automotive markets, where manufacturers competed on reliability, serviceability, and customer satisfaction rather than theoretical performance specifications. This philosophical difference extended throughout Sherman development, explaining many characteristics that German analysts identified as design compromises or inferior engineering. The modular construction, where complete bogie assemblies could be unbolted and replaced without accessing internal hull spaces, simplified field maintenance enormously, but required additional hull space and components compared to torsion bar suspensions. The standardized powertrains, where multiple engine types used identical mounting points and accessories, enabled rapid production changeovers but prevented optimization of each variant for maximum performance. The generous design margins, where components were built stronger than immediate requirements demanded, wasted materials by German standards, but provided reliability and growth potential American planners valued. Testing continued through winter 1943 into early 1944 as ordnance engineers refined track modifications and evaluated alternative approaches. The platypus grouser, a more complex design featuring T-shaped extensions that widened tracks while providing aggressive tread elements, showed superior performance in the most challenging soft ground conditions. British trials found that Shermans equipped with platypus attachments could traverse mud that stopped even the Churchill infantry tank, renowned for its exceptional soft ground mobility. American testing confirmed these results, but identified practical limitations that restricted platypus deployment. The platypus installation required significantly more labor than standard extended end connectors. Early variants demanded 326 man-hours and skilled welders to install a complete set on one tank. While the performance benefits justified this investment for specialized assault missions, the labor requirements prevented widespread deployment across entire armored divisions. Later simplified versions reduced installation time but remained more complex than duckbill connectors. Production capacity also limited availability, with experimental deliveries to European theatre units numbering only hundreds rather than the tens of thousands needed to equip all Sherman tanks. Operational restrictions further limited platypus utility. The aggressive tread elements that provided excellent soft ground traction damaged paved roads extensively, restricting tanks to cross-country movement and preventing road marches that American tactical doctrine relied upon for rapid repositioning. The extensions increased track width dramatically, in some experimental configurations reaching 37 inches, limiting ability to navigate narrow European village streets and country lanes. The added rotating mass reduced acceleration and maximum speed while increasing fuel consumption measurably. For specific missions requiring maximum mud performance, these trade-offs were acceptable. For general-purpose operations across varied terrain, standard extended end connectors offered better balance between improvement and limitations. By spring 1944, American tank forces preparing for D-Day possessed multiple track options tailored to anticipated operational requirements. Standard 16-inch tracks remained suitable for firm ground operations and road marches. Extended end connectors provided improved soft ground mobility with minimal logistics impact. Platypus grousers equipped specialized assault units tasked with breaching heavily defended positions where maximum obstacle crossing capability justified acceptance of operational restrictions. This variety reflected American approach to equipment development, providing commanders with tools suited to specific missions rather than attempting to create universal solutions optimized for all situations. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The parallel development of the horizontal volute spring suspension represented the long-term solution to Sherman flotation limitations. This system, designated HVSS in technical documentation and nicknamed Easy 8 by crews for its smooth ride characteristics, replaced the vertical coil springs of standard VVSS suspension with horizontal volutes mounted outside the hull. The new configuration allowed paired road wheels to move independently rather than in rigid bogies, improving weight distribution and providing smoother cross-country travel. More significantly, HVSS accommodated 23-inch tracks, nearly 50% wider than standard equipment, reducing ground pressure to approximately 11 pounds per square inch without any add-on modifications. Development began in March 1943, with two prototype M4A2 tanks modified for testing at Aberdeen Proving Ground by summer. The prototypes borrowed heavily from the experimental T-20 series medium tanks, an ambitious program exploring potential Sherman replacements with more powerful guns, improved armor, and enhanced automotive performance. The T-20 development contributed the basic HVSS concept, though implementing it on existing Sherman hulls required substantial engineering work to resolve mounting, clearance, and structural loading issues. Testing revealed both advantages and complications. The HVSS suspension provided noticeably smoother ride quality, reducing crew fatigue during extended operations and improving accuracy while firing on the move. The wider tracks delivered measurably improved soft ground performance while maintaining adequate hard surface mobility. The independent wheel movement enhanced obstacle crossing ability and reduced track throwing, a chronic problem where violent suspension movement could derail tracks from their guide horns. But the system proved more complex to maintain than standard VVSS equipment, requiring specialized training and different spare parts inventories. Production implementation faced challenges beyond purely technical considerations. Retooling. Sherman manufacturing facilities to produce HVSS-equipped vehicles required extensive modifications to assembly lines, welding fixtures, and quality control procedures. The suspension components themselves demanded new suppliers and manufacturing processes distinct from existing VVSS production chains. Implementing these changes while maintaining production rates meant careful scheduling to avoid gaps in vehicle deliveries to units engaged in active operations. Ordnance planners determined that gradual introduction, beginning with new production vehicles in mid-1944 while continuing VVSS manufacture in parallel, offered the safest approach to prevent supply disruptions. The first HVSS-equipped Sherman tanks, designated M4A3E8 with 76mm guns, began reaching European theatre units in December 1944. Production rates remained limited initially, with most units retaining their standard VVSS Shermans, while a few companies in each battalion received the new vehicles for evaluation under combat conditions. This gradual fielding allowed systematic collection of maintenance data and crew feedback, while avoiding the logistics nightmare of attempting to support two fundamentally different suspension types across entire divisions simultaneously. Field reports praised HVSS performance enthusiastically. Crews noted immediate improvements in cross-country mobility, particularly across soft farmland and muddy terrain common in Northwest Europe during winter operations. The smoother ride reduced the physical beating that tank crews endured during extended movements, a seemingly minor factor that significantly affected combat effectiveness by reducing fatigue. The wider tracks provided noticeably better traction in snow and ice, conditions where narrow tracks on standard Shermans lost grip easily. Maintenance personnel appreciated the ability to replace individual road wheels without removing entire bogie assemblies, though the greater number of wheels per side increased inspection requirements. But HVSS production remained limited relative to total Sherman requirements through the end of European combat operations. The vast majority of American armored divisions fought their campaigns using standard VVSS suspension, many with extended end connectors installed to improve soft ground mobility. This reflected the practical reality that manufacturing capacity, tooling limitations, and existing production commitments prevented rapid transitions even when superior alternatives became available. American industrial planning accepted this reality, focusing on incremental improvements that could be implemented within existing constraints, rather than waiting for ideal solutions that would delay equipment deliveries. The contrast with German tank development approach became stark when examining how each nation handled comparable mobility challenges. German forces faced identical soft ground problems, indeed more severe ones given extended Eastern Front operations, where Rasputitsa created mud conditions far worse than anything encountered in Western Europe. German responses emphasized radical redesigns and exotic technical solutions, rather than practical field modifications. The Ostketten, wider tracks developed specifically for Eastern Front service, required different sprockets and running gear incompatible with standard equipment, creating supply and maintenance complications. Various Panzer models used completely different track types with no interchangeability, forcing supply units to stock multiple incompatible variants simultaneously. German tank destroyers and assault guns employed entirely separate track systems from the Panzer series, despite using similar hull and suspension components in many cases. This proliferation of incompatible variants, each optimized for specific requirements but requiring unique spare parts and specialized maintenance knowledge, created logistics nightmares that worsened as the war progressed. By late 1944, German supply units reported that tracking and distributing the hundreds of unique track types, suspension components, and running gear parts consumed enormous administrative effort while failing to prevent chronic shortages at frontline units. American standardization philosophy, by contrast, emphasized maximizing parts commonality across variants, even when this required accepting suboptimal compromises in individual vehicle performance. The same basic track types served multiple Sherman models with only minor variations. Suspension components shared common dimensions and mounting methods across different hull types. This approach sometimes frustrated engineers who recognized that custom optimization could enhance performance, but it ensured that frontline maintenance units could support vehicle fleets without requiring encyclopedic knowledge of variant-specific differences or maintaining huge spare parts inventories covering every possible configuration. The extended end connector program exemplified this philosophy. Rather than developing multiple incompatible widening systems for different Sherman variants, ordnance engineers created a single connector design compatible with all standard 16-inch tracks regardless of whether they equipped M4, M4A1, M4A2, M4A3, or M4A4 hulls. This universality meant that any tank battalion could receive a shipment of connectors and install them on its entire fleet using identical procedures and tools. Field modifications in Italy, where units had fabricated their own solutions, became standardized into production items that worked identically across the entire Sherman inventory deployed worldwide. Combat operations in Northwest Europe through 1945 confirmed the value of these track modifications. The winter of 1944 brought heavy rains that turned French and Belgian farmland into expanses of mud. German forces, retreating toward their border defenses, exploited weather conditions by destroying drainage systems and flooding approach routes exactly as they had in Italy. Allied armoured spearheads found their advances slowed by terrain conditions that German intelligence assumed would be impassable to Allied armour equipped with narrow tracks. But American tank battalions deploying extended-end connectors maintained mobility across terrain that should have stopped them entirely. Unit after action reports documented numerous instances where Shermans traversed muddy fields that German commanders believed impassable, appearing in positions where no armour was expected, and disrupting defensive plans predicated on terrain channeling Allied attacks into predictable avenues. The tactical advantage gained through superior mobility the ability to maneuver where enemy planning assumed you could not, often proved as valuable as firepower or armor protection in determining engagement outcomes. German prisoners interrogated about their defensive tactics expressed surprise and frustration at American tank mobility. They had been briefed extensively on Sherman limitations, informed that narrow tracks made the vehicles vulnerable to immobilization in soft ground. Defensive positions were cited to exploit these limitations, with fields deliberately flooded to create obstacles that would channel American armor into kill zones covered by anti-tank guns. When Shermans appeared across supposedly impassable terrain, attacking from unexpected directions, these carefully prepared defenses became far less effective than German tactical planning had assumed. The psychological impact extended beyond immediate tactical situations. German tankers, already concerned about numerical inferiority and declining mechanical reliability of their own vehicles, found that even their assumed advantages in mobility were being negated by American adaptations. The narrative that superior German engineering would offset Allied material advantages became increasingly difficult to maintain when American tanks demonstrated capabilities German intelligence had confidently declared impossible. This erosion of confidence in technical superiority contributed to broader demoralization as German forces recognized they faced enemies who could match or exceed German performance across all combat dimensions. Soviet forces, receiving thousands of diesel M4A2 Sherman tanks through Lend-Lease deliveries, implemented their own track modifications suited to Eastern Front conditions. Soviet tankers, highly experienced with mud and snow operations from years of continental warfare, valued the Sherman's reliability and ease of maintenance, but initially criticized its relatively high ground pressure compared to the T-34. Soviet field workshops fabricated their own track extensions, using local materials and installation methods adapted to Soviet maintenance practices. These modifications, though differing in specific design details from American extended-end connectors, demonstrated identical operational principles and achieved comparable performance improvements. The true test of Sherman track modifications came during the final Allied offensives into Germany through winter and spring of 1945. Operation Veritable. The British and Canadian assault through the Reichswald Forest beginning February 8 encountered conditions that seemed designed to vindicate every German assumption about Allied mobility limitations. Weeks of heavy rain had saturated the ground. German engineers had systematically destroyed drainage systems and deliberately breached Rhine River flood controls, creating artificial lakes across approach routes. British commanders examining the terrain before the offensive questioned whether armoured operations could proceed at all in such conditions. Yet the Sherman tanks supporting the operation, many equipped with extended-end connectors and increasing numbers with full HVSS suspension, demonstrated mobility that exceeded even optimistic predictions. Unit war diaries recorded Shermans traversing muddy forests where German defenders had assumed no armour could possibly advance. The 79th Armoured Division, employing specialized Sherman variants including flail tanks and bridge layers alongside standard gun tanks, maintained forward momentum through terrain conditions that would have immobilized conventional armored forces. The modifications that ordnance engineers had developed on Aberdeen, proving grounds 2 years earlier, dismissed by German intelligence as crude expedients, now enabled operations that German defensive planning had declared impossible. German forces defending the Reichswald had positioned their limited armor reserves to counter expected Allied attacks along roads and firm ground corridors. When British and Canadian Shermans appeared advancing cross-country through supposedly impassable forests, German anti-tank deployments found themselves outflanked. Defensive positions sited to cover predictable approach routes became vulnerable to attacks from unexpected directions. The tactical advantage gained through superior mobility, the ability to maneuver where enemy planning assumed terrain would prevent vehicle movement, influenced engagement outcomes as decisively as firepower or numerical superiority. The Rhine River crossings in March 1945 provided even more dramatic demonstrations of Sherman mobility advantages. Engineers had developed specialized waterproofing kits, allowing tanks to ford water obstacles up to approximately 5 feet deep, sufficient for most river crossings with prepared approaches. but the techniques required reliable engines that could maintain power under partial submersion, sealed electrical systems that functioned when wet, and robust suspensions capable of operating in slippery underwater conditions. Sherman powertrains, developed from decades of automotive engineering experience and tested exhaustively under adverse conditions, met these requirements consistently. German tanks attempting similar deep fording operations suffered catastrophic mechanical failures. The Panther's complex Maybach engine, despite its impressive power output, proved vulnerable to water ingress through inadequately sealed components. Its sophisticated fuel injection system failed when submerged. The interleaved suspension wheels, already problematic in mud, became completely inoperative when packed with water-soaked debris. Shermans crossing the Rhine under fire maintained mechanical reliability that enabled rapid build-up of armoured forces on the eastern bank, overwhelming German defences before they could organise effective counterattacks. The 2nd Armoured Division's crossing at Wesel on March 24 exemplified this capability. Sherman tanks rolled through prepared ford sites, their engines roaring steadily as water surged around turret rings. Crews had applied waterproofing compounds following standard procedures, sealed vulnerable openings with techniques learned during training exercises, and installed extended exhaust stacks, allowing engines to breathe even when hull tops were submerged. The crossing proceeded with remarkable speed, entire battalions establishing footholds on the eastern bank within hours of initial assault. German defenders, expecting that any river crossing would require days of vulnerable bridging operations, found themselves facing concentrated armour before they could manoeuvre reserves into blocking positions. These river crossings demonstrated that track modifications represented only one component of comprehensive automotive excellence. The extended end connectors and HVSS suspensions provided mobility in soft ground and mud, but the complete package of Sherman design characteristics, the reliable engines, sealed electrical systems, robust transmissions, and straightforward maintenance procedures, created a vehicle that simply worked under conditions that defeated German equipment. This holistic reliability, this comprehensive integration of automotive engineering principles throughout the entire vehicle system, reflected design maturity that German military-industrial complex never achieved, despite its theoretical knowledge and scientific expertise. Field maintenance records from the final months of European combat revealed the ultimate vindication of American design philosophy. Sherman operational readiness rates remained above 70%, even during intensive combat operations involving sustained movement and frequent engagement. German armour, the few Panthers and Tiger IIs that remained operational, struggled to maintain readiness above 40%. The disparity derived not from combat losses but from mechanical failures that occurred faster than field maintenance units could repair them with degraded parts quality and disrupted supply chains. The same extended end connectors that improved soft ground mobility also simplified maintenance in unexpected ways. Because they were bolt-on additions rather than integral track components, damaged connectors could be removed without replacing entire track sections. Crews could operate temporarily with some connectors missing, accepting reduced flotation performance until spares became available, rather than being completely immobilized by track damage. This fault tolerance, this graceful degradation where partial component failure reduced capability without eliminating it entirely, exemplified practical engineering that prioritized operational availability over theoretical optimization. German track systems, optimized for maximum performance under ideal conditions, tolerated no such compromises. A damaged track link required complete replacement because the integral design prevented field repairs of individual components. The precise tolerances demanded by German engineering meant that worn tracks required replacement earlier than American equipment because excessive wear created dangerous slack that could derail tracks during violent maneuvers. The interleaved suspension wheels on Panthers and Tigers, while providing excellent weight distribution, required removing multiple wheel sets to replace inner units, a process consuming hours even under ideal workshop conditions and virtually impossible during combat operations. Soviet forces, driving westward through Poland and into Germany, demonstrated their own appreciation for Sherman mobility advantages. Soviet tank armies, equipped primarily with T-34 tanks supplemented by Lend-Lease Shermans, assigned the American vehicles to specific roles where their characteristics provided maximum advantage. Sherman battalions frequently served as exploitation forces, assigned to rapid advances exploiting breakthroughs rather than initial assaults, where heavy armor and powerful guns mattered most. Soviet commanders recognized that while T-34 seconds might possess certain tactical advantages, Shermans offered superior reliability and sustained mobility that made them ideal for deep operations, where maintenance support would be limited and mechanical failures could strand units far behind enemy lines. Soviet tankers applied their extensive combat experience to Sherman operations, developing tactics that exploited the vehicle's strengths while minimizing exposure to its weaknesses. The reliable powertrains and easy maintenance meant Sherman units could sustain operational tempos that exhausted crews before vehicles broke down, exactly the characteristic required for exploitation operations. When Soviet Sherman battalions received extended end connectors through Lend-Lease deliveries, they welcomed them enthusiastically. Soviet field workshops also continued fabricating their own variants using local materials when official supplies proved inadequate, demonstrating again that the basic Sherman design accommodated modification, using resources available in theatre without requiring factory support. The final battles in Czechoslovakia and Austria during April and early May 1945 saw American and Soviet Sherman tanks operating across mountain terrain that seemed entirely unsuited for armored operations. Narrow roads, steep grades, and frequent mud slides created mobility challenges different from open farmland or forests. Yet Sherman battalions maintained advance rates that German defenders could not match, even when retreating over familiar ground with shorter supply lines. The combination of reliable engines that maintained power on steep grades, robust transmissions that handled repeated shifts without failure, and adaptable track systems that provided traction on varied surfaces enabled operations that should have been impossible according to conventional armored warfare doctrine. These final operations provided ironic counterpoint to German assumptions from war's beginning. In 1939 and 1940, Wehrmacht doctrine had emphasized concentrated armor, exploiting breakthrough opportunities with rapid, deep advances that defeated enemies through speed and operational surprise before they could organize coherent defenses. Panzer divisions had revolutionized warfare through exactly this capability, their mobility and striking power, overwhelming Polish, French, and Soviet forces, despite often being outnumbered and outgunned. By 1945, Allied armor had turned this doctrine against its creators, sustaining operational tempos that German forces could no longer match because their equipment lacked the reliability and maintainability to support continuous operations. The Sherman tank, so often criticized during and after the war for having inadequate firepower and insufficient armor protection compared to German heavy tanks, had proven decisively superior in the one characteristic that actually determined strategic success: the ability to maintain military operations continuously without being limited by mechanical failures. German tanks might win individual engagements when they reached the battlefield operational and properly supported, but they reached the battlefield far less often than required, spending more time immobilized awaiting repairs than actively engaged in combat operations. Track development represented one component of this comprehensive reliability advantage, but an important component that influenced operational capabilities directly. A tank immobilized in mud was as useless as one disabled by mechanical failure or destroyed by enemy fire. The extended end connectors and HVSS suspensions, those simple modifications that German engineers had dismissed as crude expedients, enabled sustained mobility under conditions where German armor became stuck or damaged their running gear attempting to move. This mobility translated directly into operational tempo, the ability to maintain pressure on retreating enemies and exploit opportunities before they could fortify positions. Post-war technical intelligence programs produced exhaustive comparisons between American and German tank development approaches. Teams of American and British engineers examined captured German vehicles, interviewed Panzer designers and field commanders, and analyzed documents from German tank development offices. The resulting reports, classified for years due to their detailed technical content, documented systematically what battlefield results had already proven. German tank development had pursued impressive specifications at the expense of practical reliability. American development had prioritized operational effectiveness over theoretical performance maximums, accepting compromises in individual characteristics to achieve superior overall capability. The track development story featured prominently in these analyses as exemplifying broader philosophical differences. German wide-track systems, technically sophisticated and carefully optimized, required extensive development time, complex manufacturing processes, and incompatible components that created supply nightmares. American extended-end connectors, crude by German engineering standards, could be produced quickly by numerous manufacturers, installed rapidly using basic tools, and maintained by ordinary mechanics with minimal training. The American approach delivered improved capability to thousands of tanks within months of problem identification. The German approach produced technically superior solutions that never achieved widespread deployment because industrial capacity and logistics systems could not support their implementation. These assessments influenced post-war American tank development profoundly. The M46, M47, and M48 series tanks that equipped U.S. armored forces through the 1950s incorporated numerous design principles validated by Sherman experience. Wide tracks and low ground pressure received high priority from initial design stages rather than being addressed through later modifications. Suspension systems emphasized serviceability and parts commonality over theoretical optimization. Powertrains used commercial automotive components wherever possible to leverage existing manufacturing capacity and maintenance expertise. The emphasis on operational readiness and sustained availability, characteristics that had made Sherman successful despite its tactical limitations, shaped American armor development for decades. The contrast with Soviet post-war development proved equally instructive. Soviet designers, having examined both German and American tanks extensively during the war, drew conclusions that reflected their own operational priorities and industrial capabilities. The T-54 and T-55 series, which became the most widely produced tanks in history, borrowed elements from both approaches. Wide tracks and low ground pressure came from German practice. Automotive simplicity and ease of maintenance reflected American influence. The resulting vehicles combined impressive tactical capabilities with remarkable reliability, though they never matched German tanks in specifications nor American tanks in serviceability. German tank development, reconstituted in West Germany during the 1950s as the Bundeswehr rebuilt its armored forces, deliberately rejected many pre-war and wartime practices. The Leopard 1 development program emphasized reliability, maintainability, and logistical sustainability rather than pursuing maximum possible specifications. Engineers who had worked on Panther and Tiger programs acknowledged that their wartime designs, while tactically impressive, had failed operationally due to inadequate attention to automotive engineering fundamentals. The Leopard incorporated design principles remarkably similar to Sherman development philosophy: robust components with generous design margins, standardized parts to simplify supply, and straightforward maintenance procedures accessible to ordinary soldiers rather than requiring specialist technicians. This intellectual evolution represented perhaps the ultimate vindication of American tank development approach. The nation that had pioneered sophisticated armored warfare tactics, that had built technically advanced vehicles embodying cutting-edge engineering, eventually acknowledged that its wartime enemies had understood practical military requirements better than German designers had. The crude expedients and makeshift solutions that German engineers had dismissed during the war became guiding principles for post-war German tank development when freed from ideological commitments to technical superiority and theoretical optimization. The story of Sherman track development thus resonates far beyond its immediate wartime significance. It demonstrates how practical engineering focused on solving real operational problems using available resources can achieve decisive results that theoretically superior approaches cannot match when constrained by industrial capacity and logistics limitations. It illustrates how incremental improvement and adaptive modification can enhance equipment capabilities more effectively than waiting for comprehensive redesigns that require years of development and disrupt existing production. Most fundamentally, it proves that understanding user requirements, prioritizing practical serviceability, and designing for field maintenance by ordinary personnel creates military equipment more capable of achieving strategic objectives than pursuing impressive specifications that cannot be sustained under combat conditions. The extended end connector, that simple sheet metal extension welded to standard track links, embodied these principles perfectly. German engineers examining captured examples saw crude workmanship unworthy of serious consideration. They measured dimensional variations that violated precision manufacturing standards. They identified design characteristics that textbooks would classify as suboptimal compromises. Every technical criticism was valid from theoretical engineering perspective, yet the connectors worked. They improved mobility measurably across thousands of tanks. They could be installed and maintained using skills and tools available in field conditions. When they broke, which happened regularly, replacement was straightforward using standard procedures and existing supply stocks. These characteristics, which German technical culture identified as weaknesses, actually represented sophisticated understanding of what military equipment required to succeed operationally. The extended end connectors were not optimized for maximum performance under ideal conditions. They were optimized for maximum operational availability under field conditions where ideal circumstances never existed. This distinction between theoretical optimization and practical effectiveness determined which equipment succeeded strategically, regardless of its tactical specifications. The Sherman tank, equipped with these modifications, with its widened tracks and improved flotation, could traverse terrain German commanders assumed would stop Allied armor. This capability influenced tactical outcomes directly by enabling maneuvers enemy planning had declared impossible, but the broader significance transcended individual battlefield results. The track development story demonstrated that American automotive engineering maturity, developed through decades of civilian industry experience, building reliable vehicles for ordinary users under varied conditions, translated into military capabilities that German theoretical knowledge and scientific expertise could not match when applied through industrial systems lacking equivalent practical experience. By spring 1945, as Wehrmacht forces disintegrated under pressure from east and west, the technical debates about track design and suspension systems had become grimly academic. German armor had been destroyed not primarily through combat losses but through industrial attrition, the cumulative effect of inadequate production, disrupted supply chains, and mechanical failures that immobilized more vehicles than enemy action destroyed. American armor had sustained operations across an entire continent, maintaining pressure that prevented German forces from establishing stable defensive positions or conducting organized retreats. The difference derived fundamentally from reliability and sustainability, characteristics that track modifications exemplified, but that reflected comprehensive design maturity throughout entire vehicle systems. The final accounting revealed numbers that told the story with brutal clarity. American industry produced approximately 50,000 Sherman tanks during the war. German production of all tank types combined totaled roughly 30,000. But counting production numbers understated the true disparity, because operational availability determined how many vehicles actually fought at any given time. American armored divisions typically maintained 70 to 80% of their Shermans operational, even during intensive combat. German Panzer divisions struggled to keep 40% operational, with some units reporting catastrophic readiness rates below 25% during periods of heavy fighting or extended movement. This operational availability gap meant that actual combat power ratios exceeded production disparities substantially. An American armored division with 300 Shermans and 75% readiness put 225 tanks into action. A German Panzer division with 100 Panthers and 40% readiness fielded only 40 operational vehicles. The 3-to-1 production advantage translated into better than 5-to-1 advantage in actual combat power available for operations. Track modifications that improved mobility and reduced maintenance requirements contributed to this availability advantage, enabling American armor to maintain operational readiness that German equipment simply could not match under field conditions. German post-war memoirs and technical assessments acknowledged these realities, though often attributing them to material shortages, strategic bombing, and overwhelming Allied numerical superiority rather than fundamental design philosophy differences. Panzer commanders described fighting under impossible conditions, with inadequate supplies and insufficient replacements. They documented mechanical failures that left tanks immobilized at critical moments, noting that individual vehicle superiority meant nothing when vehicles could not maintain operational status long enough to reach battles where their capabilities might matter. Some eventually acknowledged that German tank development had pursued wrong priorities, optimizing specifications rather than reliability, seeking impressive performance rather than sustained availability. These admissions, often grudging and qualified, represented intellectual evolution from wartime assumptions that technical superiority would offset material disadvantages. The Sherman tank, so often disparaged during the war for its tactical limitations, had proven strategically decisive precisely because it emphasized characteristics that determined operational effectiveness rather than pursuing specifications that looked impressive but could not be sustained. The track modifications that enabled Shermans to traverse mud German tanks could not cross-exemplify this practical engineering philosophy, solving immediate problems with available resources, rather than waiting for theoretical optimal solutions that would arrive too late or prove too complex for field implementation. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.